let's look into the design criteria for struts, ties, and nodal zones. So for strut C star, which is your applied loading, why we have put star? Because that's the limit state for the ultimate limit state design. So C star, which is the applied compressive force on the strut, must be less than equal to the design strength of the strut, isn't it? That's obvious. I call the left-hand side is your applied force, which is the factored loading, because that's what the star is for limit state design. The right-hand side is your design strength of the strut, where C star is applied critical compressive force for all possible combinations. Don't forget the combinations, because those principles are the same what you have done for the other concrete member design. That means again you will use is 1170.0 section 4, use appropriate combinations and then calculate the factor loading and then design the struts, ties, etc. For ties, T star less than equals to U, understood, and we know that T star in this case is applied tension force. That means when you are calculating C star, T star, etc., they are calculated based on the structures subjected to the factor loading, and then you are designing against them. For node, the design strength sigma C must not exceed than the principal compressive stress at any node alpha. This is understood, because if it is exceeds, what will happen? That node is going to fail in compression. That means it will be crushed. Now let's look at briefly, because we will again come into this more detail when you do the example. At least understood the principle here. Calculation of bursting reinforcement in bottle-shaped struts. So as per clause S3600, clause 12.7, for minor degree of, you can see there's a change in clause. This is for structures which are designed using strut and time only. So what this standard is prescribing is this. You can have a different degree of crack control, and for a different degree of crack control, your stress in steel, that is sigma ST, should not exceed a certain value. So what we are trying to say, that if the stress in the steel does not exceed a certain value, that means what will happen? This will also control the steel strain. As a result, this will also control the strain in concrete. So we'll have a less chance of the cracks. You can see, this is the thing. Again, I'll repeat this one. If you limit the stress in steel, it will limit the strain in steel. It will also limit the strain in the concrete, because it limits the load carried by the steel, isn't it? That means concrete strain will also be reduced. So what standard is saying, depending on the degree of control, we will control the maximum stress which is allowed in the bar or carried by the bar. And also the spacing. That means what is the spacing that is required for that? Because you see, if you have spacing more, then you can have secondary cracks. So for minor degree of crack control, sigma ST less than equals 350 MPa, where the spacing is less than equals 350. Similarly, you can have for moderate and strong degree of crack control, the limits. Now, what the standard also says is this. When you have a moderate degree of crack control, then the cracks are inconsequential or hidden from view. Then you have this one. Okay. Now, where a strong degree of control is required for appearance or where cracks may reflect to finishes, then you go to a strong degree of crack control. Remember one thing, these requirements of crack control shall be deemed to be satisfied if the stress in the reinforcement under the short-term service load, you see, because serviceability is critical many times, and the maximum center-to-center spacing between the bonded reinforcement crossing the crack is satisfied. This following. So you can see this one, how we can provide different degree of crack control by controlling the stress in steel and the spacing of the reinforcements. So S is the maximum center-to-center spacing. Now what happens is, if you recall before, for a bottle-shaped strut, we have this problem of bursting. Now, when you have the problem of bursting, then you need to provide this bursting or the splitting reinforcement. And that's what I'm explaining here. Now, what happens is, if your bursting force is less than equals this one, okay, so then you have to provide the minimum bursting reinforcement. Now, what is this critical bursting reinforcement? It is expressed in this form. So LB, which is your length of the bursting zone, times the thickness, which is the thickness of the member. In this case, the thickness T will come. Example will explain it better. T, and then times your F prime CT. What is F prime CT? That is your tensile strength. So if you look at the clause, and B, or sorry, this, yeah, this is not the thickness, though the notation is used as thickness. It appears to be thickness, it is like this. So you have LB, say, which is your length, and this is your T. So which is your width of the cross-sectional, width of the cross-section or the member. Okay. So we'll leave this one, we'll change this one, just hold on. Okay, so what we're saying is, if you have a critical bursting force, which is across the strut at cracking, shall be given by this. Remember, this T in this case, the width of the rectangular cross-section or the member, and LB is the length of the bursting zone. Now, this F prime CT, which is your basically the tensile strength of the concrete, which is given by 0.36 times square root of F prime C. And then LB is given by this expression. Now, if you look at LB, it looks a complicated expression. What I suggest is look at this figure first, very important. Now, I could not manage to scan this one because for some reason it was the whole figure was not getting scanned. So what happens is when you read this slide, please look into this figure. It's a bit involved figure. As I've said, I'll explain it more when we will solve the problem. But at this point of time, just think in a general way. If you have a bottle type unconfined stress field, then you have to provide a bursting reinforcement in order to prevent the bursting or splitting failure. Now, what we are saying is if the bursting force is greater than equals or this 0.5 times the critical bursting force, which is given by this, then you have to provide the minimum. We'll come into that. What is that reinforcement? Now, these are some standard notations we have used. Now, what the clause 7.2.4 is saying that the bursting is provided either in two orthogonal directions at angle gamma 1 and gamma 2 the axis of the strut, or along one direction at an angle gamma 1 to the axis of the strut, where gamma is greater than 40 degrees. Now, we have seen this one before, isn't it? So this is the same way we can provide that. And we are also saying that for strength, we have this criteria has to be followed. So phi ST times sigma SI means that is the steel provided times FSY yield strength of steel times sine gamma 1 or sorry sine gamma I. And for serviceability, you have another expression which is the right hand side is different. Can you see that right hand side is the standard says we have to have the serviceability, the bursting force due to the serviceability loading. And then there's a critical bursting force, which we are talking about before. You know, remember this bursting one, this TBCR. And this bursting force is calculated by this, where C is actually the compressive force. So TB is calculated by C times tan alpha. Now, what people have observed is that for serviceability, tan alpha is your half. And for strength, tan alpha is actually much less, which is 1/5. Okay, simply because what we see is that for serviceability, you can see that the cracks are, the bursting force is much higher. So once you allow some of the cracks, then automatically what happens is that effect reduces, and as a result, you get a less value of bursting force for strength. For example, if you think of a divergent stress field, so the divergent stress field will increase if there is no crack. Once cracks start appearing, then automatically that divergent stress field will be more like a prismatic one. And as a result, when it comes to strength, we get a less effect of the bursting force. Now the design procedure: develop a Strut and tie model for the structural concrete member, either using load path method or PBO technique. Calculate the axial forces in struts and ties based on critical combinations of factor loadings as per as 1170.70.0 and clause 2.4. Check the bearing capacity of loading points and supports. Very important. Check the capacity of struts and nodal zones. Determine steel reinforcement for tension ties. Determine minimum steel reinforcement for crack control or even bursting. Bursting can be a problem. Detail the layout of steel reinforcement. Okay. So this is, in a nutshell, is the design procedure. So you can see that there are lots of steps involved, but as per the real design steps, they are much simpler in this case, but much more complexity is first to develop a proper, Strut and tie model, and then analyze the Strut and tie model, and then design all the components. That means struts, ties, etc. Design a deep beam. This is your example 6.2 in study book. That's the example problem. And then references, yes, chapter 7 of your textbook and AS3600 2018. Any question? Yeah, I will quickly make a comment before I stop, that when you're looking at the bursting force, remember, if you think your plane of the screen, right, you have this strut. For example, this is strut, right? And then you have somewhere you have this bursting is happening because we have this, reduction in this area. Yeah. So change in the cross section, basically, it's getting divergent type of stress field. Then what happens is your LB will be the length of the bursting zone, so which is in the plane of your screen. But when you look at the T, that is basically the width of the member. So width of the member means in this case that is actually perpendicular to the screen, and that is your T. So that's the width of the member. Okay, so don't get confused with that T here, with the term T, that it is the thickness. Okay. So I'll stop here and look up the example problem. This is very important, the example problem, and then solve tutorial problems. Thank you.